Welcome back to today's lecture. We're going to be looking at Unit 3, which is Basic Logic Gates. And when we talk about logic gates, they are basically electronic circuits that we use in implementing a lot of logic expressions, which we normally term as Boolean expressions. Now, when we talk about combinational logic, we're looking at basically logics where we use different examples of logic gates together to perform a certain function. So the basic building block for a combinational logic would also be the logic gate. Now, when we take the logic gates in general, there are three basic logic gates. That is the OR gate, the AND gate, and then the NOT gate. Now, from these three basic logic gates, we can derive some other logic gates like the NAND, which is a combination of the NOT gate and the AND gate. Then we can also have the NOR gate, which is a combination of the NOT gate and the OR gate. Then we have the exclusive OR gate, and then we also have the exclusive NOR gate. Now, in this unit, as we look at logic gates, we're going to look at this with the help of truth tables and Boolean expressions. Boolean expressions in the sense that these logic gates would normally have some inputs and we expect to have some outputs. So the output would be an expression of how the inputs are processed by the logic gate. Now let's look at the learning objectives or the learning outcomes of this unit. It is expected that by the time we are done with this unit, you should be able to describe the operation and construct truth tables of an inverter. That is the NOT gate, the AND gate, and the OR gate. You should also be able to describe the operation and construct truth tables of NAND gate, the NOR gate, the exclusive OR gate, and then the exclusive NOR gate. You should also be able to express the logical operation of an inverter, an AND, OR, NAND, NOR, XOR, and XOR gates in terms of Boolean equations. Then finally, you should be able to use these logic gates to implement a circuit represented by a Boolean equation. So let's look at some common logic terms. Now, since we're dealing with binary, we would normally have bits to deal with. Now, when we talk about the logic 0, that is the binary bit 0. This can also be termed as false. That also means off, low, no, or an open switch. Then for logic 1, corresponding that to the logic 0, logic 1 is true, on, high, yes, and then closed switch. Now, we would also need to understand something we call the truth table. A truth table basically lists all possible combinations of input binary variables and the corresponding outputs of a logic system. So when we talk about a logic system, which will normally give us an output which will term as a Boolean expression, depending on the number of bits that are at the output, we would normally have a certain number of bits in the input that will give us certain possible combinations that will result in a certain output. So for instance, if we have only one variable or only one bit, then it means that we can have only two possible combinations. That will mean that we have 2 raised to the power 1, which would give us what? 2. So this would give us 2 possible combinations, that is either a 0 or a 1. Now, if we have 2 bits, which is 2 raised to the power 2, because we're dealing with binary, then we would have 4 possible combinations. So the first combination will be 0, 0. The next combination will be 0, 1. The other one will be 1, 0. And then we'll finally have what? 1, 1. So these are how truth tables are generated. So for instance, when we take this logic system, for instance, where we have input A and input B, and then an output Y, because the inputs here are 2, we would have 2 raised to the power 2, which would give us 4 possible combinations of A and B. So for A and B, you have 0, 0 as the first combination. Then the second combination, you have 0, 1, 1, 0, and then 1, 1. What this is basically representing in a decimal system is 0, 1, 2, and what? 3. So this would give us some possible output depending on the logic operation. So similarly, if it is a 3-input logic system where we have A, B, and C with a corresponding output Y, this will mean that we are looking at 2 raised to the power 3, which is 2 times 2 times 2, which is basically equals to 2 times 2, which is 4, times 2, which is what? Equals to 8. So it means we can get 8 possible combinations. So starting from 0, you have 1, you have 2, you have 3, 4, you have 5, you have 6, and 7. So these are 8 possible combinations of 3 bits. And then you would have the corresponding output in Y. So this is basically what we term as a truth table. So what we can say in general is that if a logic circuit has n binary inputs, each truth table will have 2 raised to the power n possible input combinations. or in other words, we can have 2 raised to the power n rows. So please take note of that as we progress. Now, what are logic gates? As in the introduction, I earlier on talked about logic gates, and then I said they are the basic building blocks of any digital system, even including computers. Okay. Now, each one of these logic gates is some piece of hardware or an electronic circuit which would normally be used to implement some basic logic expression. Whilst laws of Boolean algebra could be used to do manipulation with binary variables and simplify logic expressions, these are actually implemented in a digital system with the help of electronic circuits called logic gates. And like we said earlier on, the 3 basic logic gates are the OR gate, the AND gate, and the NOT gate. Now let's proceed to look at these logic gates one by one. An OR gate performs an ORing operation on 2 or more than 2 logic variables. So when we take an OR gate, this is the symbol of an OR gate. It's a 2-input logic device and a single output. But there can be instances where an OR gate would be capable of processing more than 2 inputs. So you can have a 3-input OR gate. Now, the OR operation on 2 independent logic variables, that is A and B, is written as y equals to a plus b. And if we're reading that, we'll read it as y equals to a or b, and not normally a plus b. The output of an OR gate is low only when all of its inputs are low. So for any other combination of inputs, the output is always high. So let's take this truth table for instance. Where we have A and B as the inputs to the logic gate, where we have an output A or B. What we're basically trying to say is that the only time you would find the output of an OR gate being 0 or off or low or false is when the inputs are both 0. But for any other combination, the output is always 1 or high or on. So you would see that for these inputs here, where we have 0, 0, the output is what? 0. Where we have 0, 1, the output is 1. Where we have 1, 0, the output is 1. Where we have 1, 1, the output is what? 1. And similarly, when you look at the truth table for the 3-input OR gate, you will see that we only have an output of 0 when all the inputs are 0. but for all other inputs or input combinations, the output is what? 1. So kindly take note of that. Now, let's look at an example of what an OR gate can be used for. So when we take a basic alarm system, which is measuring temperature as well as pressure. Now, we have a comparator. The comparator will mean that within the comparator, there is a threshold voltage that has been set. So the other input of the comparator would also be a certain voltage. So at all times, the comparator compares its inputs and then gives an output. Now, because we're using an OR gate and connecting that to the alarm, when the inputs of both comparators are low, we would not get any output. Now, when the output of both comparators are low, that is when the inputs of the OR gate are low, the output that goes to the alarm is always off, so the alarm will not sound. But once there is a variation in input, that is output from the comparator, then the alarm would sound. So this is an example of how an OR gate can be used. Let's now look at an AND gate. It is also a logic gate with 2 inputs and 1 output. And in this case, for an AND gate, the output is high only when all the inputs are high. So for any other combination of inputs, the output will always be what? Low. Now, the AND gate symbol is represented by this. And the output expression for the AND gate in this case is Y and B. Y equals to A and B. So for a 2-input AND gate, where you have 4 possible combinations of input, where there is 0, 0 as input, the output is what? 0. 0, 1, the output is 0. 1, 0, the output is 0. You would only get an output of 1 when all the inputs are 1 or on or high or true. Similarly, for a 4-input AND gate, the output would be Y equals to A and B and C and D. And this gives us the corresponding truth table as you see here. The next one we would want to look at is the NOT gate. The NOT gate is a 1-input, 1-output logic gate whose output is always the complement of the input. That is, the output is always the inversion of the input. That is, the output is always the opposite of the input. So if the input is low, it means the output will be high, and vice versa. If the input is 0, the output will be what? 1. And because a NOT gate is basically a single input logic device, we can only have two possible combinations of inputs, either a 0 or a 1. So when we look at the NOT gate symbol, we have this as the symbol of the NOT gate. So you have X as your input, and then Y being the output is equal to the complement of what? X. It can also be written like this. That is the symbol or the diagram for a NOT gate. So the truth table here, we can only have two possible combinations of input, and then we would also have the output to be the complement of the input. The exclusive OR gate, which is commonly written as the XOR gate, is also a 2-input, 1-output gate. Now, the figure you see here is basically the image of an exclusive OR gate or an XOR gate. Now, the basic principle underlining the the exclusive OR gate is that if odd numbers of 1 are present at the input, then the output becomes 1. So when we look at the truth table here, because it has 2 inputs, you have 4 possible combinations of A and B. 0 XOR 0 is 0. 0 XOR 1 is 1. 1 XOR 0 is 1. 1 XOR 1 is 0. So another side of it is that the output is 0 when the inputs are identical. But when the inputs are opposite, the output is always high. So take note of that. Now, let's look at the NAND gate. The NAND gate is basically a NAND gate plus an OR and a NOT gate. So the NAND gate stands for NOT and AND, or an AND gate followed by a NOT circuit. So what will happen is that whatever the inputs produce as output for the AND gate, the NOT gate will provide a complement of the output of the AND gate. So the expression would always be Y equals to A and B complement. So in this case, you have AND gate with a NOT gate at the output. So whatever these inputs are, because they are performing an AND operation, their outputs would be complemented. So if we take 0 and 0, which would normally be 0, because there is a NOT gate, which makes it a NAND gate, we would get 1 as the output. 0 and 1 would normally be 0, but its complement is 1. Similarly, 1 and 0 would have been 0 if it were just the AND gate. But because it's a NAND gate, the output is complemented. So we would get 1. And then 1 and 1, which originally would be 1 for AND, now becomes 0 because it's a NAND gate. So assuming we had a 4-input NAND gate, what it will mean is that we have inputs A, B, C, and D. The Boolean expression for that NAND gate would be Y equals to A and B and C and D complement. Then we have the NOR gate. Like I said earlier on, these are just combination of logic gates. So in this case, it's a combination of an OR gate and a NOT gate. So you have an OR gate and a NOT gate. So the output would be Y equals to A or B complement. A or B complement. So whereas if it were an OR gate, the output would have been 0, 1, 1, 1. Because there is a NOT gate, which makes it a NOR gate, the output becomes the complement, which is 1, 0, 0, 0. So if we similarly had more than a 2-input NOR gate, we would have an expression where Y is equals to A or B or C or D complement, as we can see in this Boolean expression. Now let's look at the exclusive NOR gate or the XNOR gate. What this means basically is that we are combining an XOR and a NOT gate, and that is what gives us an exclusive NOR gate. What this basically is that whatever the inputs of the exclusive OR gate is, at the output, a complement is found. So in this case, with a 2-bit exclusive NOR gate, where you have A and B as inputs, the output will be Y XNOR B or Y XOR B complement. So in this case, we would have 0, 0, which ordinarily would have been 0 to give us 1 because of its complement. The combination of 0, 1, which would have ordinarily given us 1, is being complemented to 0. 1, 0, similarly, is complemented to 0. And then 1, 1 is also complemented to 1. And then this truth table you find here is basically a truth table for a 3-bit input XNOR gate, where the possible combinations are 8. Now let's look at describing logic gates algebraically. Any logic circuit, no matter how complex they are, we can describe them using the 3 basic Boolean operations because of the OR gate, the AND gate, and the NOT gate. Because these are the basic building blocks of any digital system. So for example, let's look at the diagrams or the illustrations here. In this first diagram, we have input A and input B, and this is an AND gate. So its output is A and B. Then we have an OR gate, which takes A and B as input, and then C also as an input. But in this case, it is an OR gate. So the output X now becomes X equals to A and B or C. So the whole of this is expressed against what? C. Similarly, if this were to be done in the opposite direction, where you have an OR gate and an AND gate, would have A or B, and this would now become the input to the AND gate, and then we'll get our X to be equals to A or B and C. So we can describe logic circuits algebraically because every logic circuit would normally contain these 3 basic logic gates, or a combination of the 3 basic logic gates. Now, like we looked at earlier on, where we talked about the NOT gate, whenever an inverter is present in a logic circuit diagram, its output expression is simply equal to the input expression with a bar over it. So when we take this diagram here, where we have a NOT gate and an OR gate, what is happening here basically is that this input, which goes through the NOT gate, has a bar on top of it, which shows that the input A has been inverted. So the output is an inversion of the input. And then once this is to be expressed with a logical expression, X will now become A bar or B. Note that the bar is only on the A, not on both of them. So it is only on the A, and that is odd with the B. These are some examples of circuits containing inverters. So here, because the inverter is at the output of the OR gate, the whole output is what? Inverted. Here, because all these three inputs, it is only the A that is inverted. You have A bar BC. And then similarly, wherever there is a NOT gate, the output of that input to the NOT gate is inverted. And that gives us a certain word expression or Boolean expression. So you take note of this as we deal with logic circuits and having to express them algebraically. Now let's look at using logic gates practically. You would find logic gates designed as integrated circuits. What they do is basically they contain equivalent miniature resistor, diodes, and transistor circuits. And a popular type of such ICs is what is illustrated here. That is the dual inline package IC. And this is an illustration of a 14-pin dual inline package IC, where the pins, you have 1, 2 in the anti-clockwise direction all the way to pin 14. And you will see that this dual inline package IC, which is 7408, has 4 sets of AND gates, which could be used to perform any logic circuit operation. And then there is pin 14, which provides the power supply. You have pin 1 and 2, which are inputs. Pin 3 is an output. 4, 5 input, 6 output. We have the ground at pin 7. We have 9 and 10 as inputs, 8 as an output, 12 and 13 as inputs, and then 11 as an output. So this is an example of a practical logic gate. And as engineers, when you have to use logic gates, you can only find them in ICs or integrated circuits. So this is an implementation of an AND gate. So here you would see that pin 14 is connected to input A and input B. And then similarly, pin 7 is connected to what? The ground. Now, the negative side of these switches are connected to ground. Then the supply is given to what? The VCC. And then the switches are also connected to the supply. So pin 1 and 2 are inputs to the AND gate, and pin Y is an output which is connected to an LED. So what will happen here is that because it is an AND gate where we have two inputs, we have 0, 0, 0, 1, 1, 0, and then 1, 1. What is going to happen here is that because it is an AND gate, we're going to have 0 and 0 would give us what? 0. So this LED would continue to be what? Off. 1 and 0 and 1 would continue giving us what? 0. So this LED will continue to be what? Off. 1 and 0 would also give us 0, and the LED will still be off. But 1 and 1 would be 1, and that is where this LED gets turned on. Now, this resistor you find here is basically a resistor just to help ensure that the proper voltage is applied to the LED. So all this is what I have just explained. So you have input A and B. Ground is basically when the switches are all off. Ground, positive 5 volts is when input A is off and input B is on. So the output would also be what? Ground or off, and there will be no light. When you have positive 5 volts and ground, similarly you get the same output. But where you have positive 5 volts, then the output voltage would be almost 5 volts, and that would give us a lighted LED. So that is basically a practical example of logic gates, or the usage of logic gates. Now, these diagrams you see here are practical examples of dual inline packaged OR gate and NOR gate. Sorry, NOT gate. So 7432 is an OR gate, and then 7404 is a NOT gate. So this brings us to the end of today's lecture. If you have any questions, feel free to put them in the comment section, and then we can get interactive there. Take a minute to subscribe to the channel and like the video so that anytime there is a new video, you can always get a notification to come back and learn something new. Until then, see you in our next lecture. Bye.